Hello and welcome. I am very excited to share our work with you. Our paper presents a methodology for accurate and robust thrust estimation on small-scale turbojet engines using limited and low-quality measurements, which is often the case for these engines. Our approach is quite simple. First, we use our testbench data and insights to construct a gray box model. Then we design an extended Kalman filter around this model that can estimate engine thrust. The context of this study is the Iron Cub, which is an aerial humanoid robot powered by 4 turbojets. So why do we need accurate thrust estimates? Well, in the control problem of the Iron Cub, the thrust is defined as a state that is controlled. And the lower the state estimation errors, the higher the control gain margins we get, which is crucial for good tracking performances and stability. Let us now dive into the state of the art. We are studying small-scale turbojets like these in which the measured states are limited and the measurements are often low resolution. Several models in literature have been explored that connect the measured states of the engine with the unmeasured states. However, a methodology that considers the model and measurement uncertainties and also accounts for engine failures to give accurate thrust estimates is lacking. This is the gap that we want to address. So we start with the model identification experiment in a custom test bench where we apply input signals and record the responses. The thrust is measured with a strain gauge sensor and the signals collected are filtered offline. The measured quantity that has a direct relationship with engine thrust is the shaft speed. For subsonic engines with low expansion nozzles, the thrust can be expressed accurately by an instantaneous function like this one. However, this model relies on the shaft speed measurements that have low resolution and are also affected by sensor dynamics. So let's find out how the shaft speed behaves. From our insights, we figured out that the control structure of the ECU is as follows. The input signal U is mapped to a desired value of RPM, which is achieved through a feedback loop. We want to explore the relationship between the input signal and the shaft speed. Looking at the step response, we decided to model this relationship with a second-order nonlinear state space representation. The steady-state behavior is known by our knowledge of the transformation between U and omega desired, so only the dynamics have to be identified. For this, we use a state-of-the-art technique called SINDI to arrive at a gray box model. Here is how the model performs on the validation dataset. Now, we want to design an EKF that fuses the model along with low-resolution shaft speed measurements to obtain a smooth estimated shaft speed, which can be transformed into estimated thrust. We want the EKF to deliver smooth and accurate results even during engine failures, so we exploit the parameter estimation algorithm. Basically, we allow this parameter, omega idle, to be estimated online by the EKF by passing it as a state. So whenever an engine failure happens and the RPM drops, the EKF observes this and modifies the value of omega idle. This way, we can get smooth and accurate estimates under all circumstances. The design EKF performs remarkably well on the test bench, so we decided to deploy it on the Iron Cub. Also, during an engine failure event, we observed that the EKF still delivered accurate estimates. And that's all. Future work would involve creating high-fidelity models for the turbojet to bridge the sim-to-real gap and characterize the performance of turbojet under varying atmospheric conditions, where the umbrella objective is to make the Iron Cub fly. Thank you.